Hi. What we've been examining was the sequential circuits. We have seen here the general form of the sequential circuits, and then we're going to examine now the sequential circuits modeling, how to model them. What I mean by saying model, if you know the model of a circuit, then you can say the behavior of your circuit without looking at your circuit. That is modeling. So you might say that if you give me the input, what the output your circuit is can be set by these models. So that's why we call them model. So there are three types of models that we will be using. This is one of them is the mathematical modeling. The other one is the state table model, and the third one is the state diagram model. In here also we're going to see another representation of the general sequential circuits form in different view. Let's come out of this page and reorganize the open board. I need to do some setting here. Open board, open board. Okay, here you are. The first is the mathematical modeling. What we've got here in this modeling, we have the input variables here, independent variables. And also we said the other independent variables are the present state variables. These are the present state variables. These are independent ones. So independent variables, input variables, state variables. Now it says the number of state variables are, so but it says n states, number of state variables, that should have been r. That small n should have been replaced with r. So what it says is this: you've got n number of input state variables, and you've got r number of state variables, small y, small yr. So I have shown these variables on this general format of the sequential circuits. What are the dependent variables? Let me show them in red color. That is the output of the sequential circuit. So we are considering the sequential circuit as this box. So that is that red thing here is the output, and that green thing here is the input. So this is independent variable. This red thing here is dependent variable. This small y is also independent variables. The other dependent variables are the next state functions. So here you are, dependent variables, next state functions, and the output functions. Why we are saying these are the dependent variables? Because we said this is a combination circuit. The small y's comes in as the input, and these are the input variables. Some part of this combination circuit goes into the memory elements. So these values here depends on that small x and small y's. Small x's and small y's. So according to these input, memory element is going to work and give you an output. According to the definition of these memory elements, you're going to see this capital Y's in terms of small x's and small y's. So these are called next state functions. Next state functions, dependent functions, and output functions. These are independent state variables, represent present state. Present state. So if you write those, it's going to be like that. This z functions, capital 1, z. We've got m number of z function. So 1, 2, 3, 4, m. Let's say f1 function is going to be a function of these independent variables. What are they? x1 to xn. Let me write it in green now. x1 point xn. So that is this. And small y's, so y1, yr. So this is this. Okay. So it goes like that up to function m. So this is the same. These functions are called output functions. And we said also we've got next state functions here. We show these next state functions as y1, and we've got r number of these functions. R is the number of memory elements because each state variable is representation of the memory element. So these are the g functions of the gm are going to be once again the function of these independent variables. What are they? Input variables and the present state represented state variables. So if you know, these are called next state functions. So if you got these functions, that means output functions plus the next state function, these functions represent the behavior of this sequential circuit. That's why we call this mathematical model, because of this function type of representation. So if we apply this to a full adder, we can write these output functions at the next state functions for this full adder. Full adder, you see, it is the simplest serial adder. So what we had in full adder, let me write it as carry in x1 and x2 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So sum here, in this case, is my output function. Sum, this is the carry out, which is capital Y. This is small y, present state. So carry values, and this the carry out, which we keep in our mind for the next bit to come to be added. So carry out, that is. So the sum is 0, carry is 0, sum is 1, carry is 0, sum is 1, carry is 0, and sum is 0, carry is 1. In here, sum is 1, carry 0, sum 0, carry 1, sum 0, carry 1, sum 1, carry 1. So these are the function. Now this function is the output function. And this is the next state function. You might call it a carry out function. So these two functions is the representation of a serial adder. If you write this function in this form, this is the canonical form. So these are the functions that we are dealing with. So 1-bit serial adder circuit mathematical model is this truth table or these functions. You can give it as a truth variable like that, or you can write this function. So this tells me that if you give me an input and tell me the present state, then I can tell you what the output is without knowing what is inside in my circuit. Just by knowing this mathematical model, I can tell you the output. That's why it is called mathematical modeling. So the next modeling is the state table modeling. Is the same thing that we represent, the same thing we have as mathematical modeling is going to be represented in a different way as a matrix form here. In this matrix form, the rows represent the present states. So we've got y1 yr, the number of state variables, independent state variables. And in the, so how many of them? So 0, 1, permutation of zeros and ones as r's, it's going to be 2 to the power n number of rows we are going to see here, isn't it? Starting from 0, 0, up to 1, 1, 1. In the columns, we've got the inputs. As you remember, we had in general x1 point point xn. These are the state input variables, independent input variables. So how many of those start from 0, 0 up to 1, 1, 1? So that is 2 to the power n number of different inputs that we could apply to our sequential circuit. Each input here is represented by a column. So here that p is 2 to the power n. So this is now in here in the columns we've got independent x variables, and in the rows I've got independent small y variables. Inside of this we are going to write these functions here. I'm going back, so I'm not going to repeat these. So this function, so that means for each x's and small y's, that is small x's, small y's, there's going to be a z function, z1 up to zm, and then there's going to be next state function from y1 to yr, capital Y1 to capital YR. So we're going to write all this inside this entity here. The first one is the next state functions, y1 point yr. The second thing, that there's a comma in between, the output function z1 point zm. These function values are going to be written in this entity of this matrix. If you write so, this is going to be a state table representation of a general sequential circuit. So if we apply this to state table representation to a 1-bit summation circuit, that means full adder. So you could see it now. Carry, we've got one carry variable, 0 or 1, and we've got two independent variables to represent the numbers x1 and x2. So if you, let's say now, consider this y1, that means carry is 1, and my input is 1, 1. So that means this, isn't it? Carry is 1, input x1 is 1, input x2 is 1. When you sum them up, 1, 1, 1, you're going to end up with this. So this is the sum, that is the output. Here you are. When 1, input 1, 1, output is 1, and this is the carry, so that is capital Y1. So I'm going to put that capital Y1. Let me change the color. Here, capital Y1. So this wasn't so nice. I make it nice looking now. So this is capital Y1. I am talking about this capital Y here. So this one is sum, that is Z, that is this Z. Values you see, 1, 1, 1, 1 here. So you can fill all this up like that. So if you fill all this like this, that means if you give me an input, this input for the numbers to be added, and give me the present state, from this table I can tell you what the output is. Let me do an example. So the example that we already used, that was this one, 12, 0, 1, 1, 0, 0, and 14, 0, 1, 1, 1, 0. Add them up. So I am saying I can find now this Z function here. I can find this carry function as well here, from here. So if it is the first thing to be done, so input is 0, 0, input is 0, 0, and present state is 0, that is 0. My output, which is Z, also it is sum as well, is going to be this. Okay. My carry is this, isn't it? So the carry that I am going to do. So that is the carry. Now my present carry for this input is once again this 0. And I'm going to apply 0, 1. I'm going to apply 0, 1. So I'm going to observe this one now for the second time as the sum. My carry is 0. So if you continue like that, so I can number the outputs that I'm going to observe. This first, and that one is the second. So if you go like that, you're going to see you're going to end up with 26. So you do it yourself. The third model is called state diagram. In the state diagram, what we do, so once again we're going to represent the output functions, which are f1 up to fm, and the next state functions, capital Y1 to capital YR, G1, point GM. The variables are going to be x1, xn, small y1, small yn. So similar thing goes here. So that's going to be here and here. So this is the mathematical model of a sequential circuit like that. So I am saying this mathematical model can be represented with another model which is called state variable. In the state variable, we represent each state as a circle here like that. So we write inside the present state variables values, so y1, yr. So let's say this is D1 state, call it present state. So one of the permutation for which we represent this y1 yr present state. That's the present state. These small y's values are going to be written inside this circle. Okay, now if you know this, that means present state. If you apply the input, you're going to get this Z output. In this diagram, what I do is write this X input as here that G. In Turkish, G is girish, that's why that G comes in. But this is in here, X1, Xn values. Whatever the values, I'm going to write it here. And there is a dash here. That is the output. Output is the Z function. These functions, so you know the present state, that means you know the small y's, you know the input, that means these x values, then you can find all the dependent output functions values from Z1 to Zm. So you're going to write all this in that Zm after the dash. Similarly, these next state functions represent another state, isn't it? So you've got here present state, that means y1, I, yr, and you've got an input x1, xn here. So if you know the present state, that means this. So if you know the input, that means this. From this next state functions, you can find the next state. So that present state goes to the next state, and we write an arrow, and there's a line between this present state and next state. That arrow tells me we go from present state to the next state. So if you draw this, then this diagram is going to be called state diagram. If we do an example, then you understand it much better. So if you remember the full adder, we had carry in or small y, isn't it? That's present state value, and x1 and x2, and z output, which is sum, and the carry out, which is capital Y. So that was, this is not 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So the output are sum is 0, carry is 0, sum 1, carry 0, sum 1, carry 0, sum 0, carry 1, sum 1, carry 0, sum 0, carry 1, sum 0, carry 1, sum 1, carry 1. Now, randomly, I am going to choose you one line here, and how this line is transferred to the state diagram here. You see that D1, make it a bit bigger. How can I see that? One more. Okay. So this is, can I do that? Maybe I can do that. Okay. Keep this up. No, okay. Here we are. Okay. Now, if we go in now, you see that is now, so this line here, present state is small y, small y value is 1. So that is 0, that is 1. So I am here, small y. And my input is 0, 1. My input is 0, 1. My output is 0, that's my output. My next state is 1. So present state is 1, next state is 1. So this circle comes back. So if you look at this one, if my present state is 0, if I apply 1, 1 it is, isn't it? My present is 0 and I apply 1, 1. Now this case, my present state is 0, that 0, is that 0. And you apply 1, 1, that means you apply this 1, 1, and that's input, as we said here. So this is x1, x2 value. And my output is 0, so the z is output here. Let me, different color. So this output here, 0. So that's that output. What is my next? That is present state, small y. That is capital Y, that's next state, is 0. My, my next state is 1, isn't it? So we'll make it different color. So my present state is 0 here. My next state is 1 here. So my present state 0, goes my next state 1, and the arrow here not seen, but I'll put that arrow in. So there is a line in between. So what I am saying is this. Once you know this table, you can transfer this table to a state diagram like that. When you transfer it state diagram like that, then I am saying we could use this state diagram as a model. So I'm going to use this model to do a summation of two numbers. So this is the one that we used. Let's say 0, or let's make it this one. 0, that's 12, and that is 14. 12, 14, add them up. So present state is going to be 0 here. Now I am using this state diagram model in order to give you the output of a sequential circuit while the input is 12 and 14 in serial. So it is like that, x1 and x2. x1 is 12, x2 is 14. Now I am saying my present state is 0, my input is 0, 0, my input is 0, 0, my output is 0 here. That is the first thing you're going to observe at the output. What is my carry? Carry is 0, so this carry is going to come here. So add them up, sum is 1 and carry is 0. So my present state now 0, and I apply 0, 1. 0, 1 is this one. My output, second output that I'm going to observe is this. My next state is 0, so it goes back to 0. My next state is 0. So this becomes present state for the next bits to come. So in the 0 state, if you apply 1, 1, that means you apply 1, 1. What you're going to observe at the output is this third one. Okay, when you add them up, sum is 0 and carry is 1. Now my carry is 1, so that means my next state is going to be 1, which is this one. That's why I put a arrow here on this line to tell us that my present state is 0, and I apply my input 1, 1. I observe output at 0, and my next state become 1. So my carry became 1. So now my carry is 1. I am in this state now, and I am applying 1, 1. When you apply 1, 1, this is the output that you're going to observe. That is the fourth output that you're going to observe. When you add them up, sum becomes 1, which is this, and my carry is 1, which is this, came on it. And this carry is going to be the present state for the next bit to be added come. So when you apply 0, 0 input, so that is the last output that you're going to observe. So if you write what you observed in an order, the first output is 0, the second output is 1, third output is 0, fourth output is 1, and fifth output is 1. So that's 26. When you add those two is 26. So what I have done here, I have represented a state sequential circuit by a state diagram, and this state diagram is the model for that sequential circuit. So the last slide tells us another way of showing the sequential circuit. You can show it like that in general, or you might show it like that. these are representing the same thing. So you have a combination circuit here, input of your combination circuit input variables, and these are the state variables here, state variables, coming the output of the memory elements applied to the combination circuit. Output of the combination circuit is my sequential circuit output. So these are Z's. So these are X's, and this is small y and capital Y's. So in here, maybe it is not easy to see here, but you might see it is here a bit better. There is a feedback here, you see, and you see the combinational circuit output has two groups. One of them goes to the output of the sequential circuit. The other combination circuit's output becomes the memory element's inputs. The memory element output is a present state or next state representation of the state variables. So if there is a central clocks for these memory elements, clock pulses like that, it is synchronous sequential circuit. If there is no central clock, so this is a sequential circuit representation, but this is asynchronous, there is no clock. That is the end of this video then.